Hello, my name is Katy, and today we'll be talking about creating porous polymers through reactive dissolution and gas evolution. So, why do we care if polymers are porous or not? Well, polymers are an integral part of our lives. While fully solid polymers can be used for several purposes, porous polymers are useful for the reduction of material cost. With proper cross-linking, structural strength is maintained. Porosity itself also increases surface area, thus improving sorption capacity. Microporous polymers of micron or submicron size are the interest in separation media. So how are they made? Let's look at the method section. Typically incorporating the porogen substance with the monomer in a homogeneous solution. As the polymer forms, the porogen separates, as droplets in a separate phase can be washed out with a solvent that won't dissolve the polymer. In this process, the porogen is a solid particle of micron or submicron size. After polymerization, it is removed by reactive dissolution that leaves a void where the particle once was. We show initial results from experiments where a hyperbenching polymerization system incorporates calcium carbonate particles. After polymerization, the polymer is treated with dilute acid, which dissolves and removes the particles with simultaneous evolution of carbon dioxide. So what did we do? What did we use? We used a 5000 VHX digital microscope, calcium carbonate, methylamine, BDDE, and polystyrene petri dishes. The experiment itself, we used a mixture of 2.8 methylamine, 7.2 BDDE, and water. We separated that and made the calcium carbonate solutions with different weight by volume percentage, 0.26, 2%, 6%, and 10%. 50 microliters of each mixture was placed in a sulfonated polystyrene petri dish and placed in 80 degrees C overnight. After the polymers was set, it was stained with eosin and dyed for 5 minutes, then washed with isopropanol to remove any of the excess eosin. The stained polymer washed with acetic acid for 1 minute was the very last step, and that gave us the current results that we see now. We have the control, the 0.26, the 2, the 10, and the 6. We can see that the color before the acid is definitely a lot pinker than after the acid. We can see that it is a lot more detailed in the 6% calcium carbonate concentration with all of the pores and molecules in this area right here. So what does this mean? MA/BDDE polymer is a positively charged anion exchanger. It is stained pink by the anionic dye eosin. In the acid, this takes a yellowish hue. When the acid cannot access as easily as the polymer's interior, the pink intensity may decrease. On a prolonged exposure to acid and access to the polymer interior, facilitated by the pores, eosin bound to the polymer is washed off. This means that both the morphology of the polymer and its apparent color offer a short acid wash provides clues to the polymer structure. This method can be used to test ion concentrations in water samples, earth samples, and even interplanetary soil exploration. So what's next? We will be using this method to make an anionic change in open tubular columns, which ion separation capacity depends on. To conclude, with increasing calcium carbonate content in the prepolymer, both porosity and pore size of the polymer increase. The resolution of the present microscope is insufficient to reveal the pore structure at low calcium carbonate concentrations, but clearly shows that acid wash can remove the particles completely. We will be investigating in the future with the assistance of the electron microscope for some images with calcium carbonate grinded at a much finer scale. Let me show you a quick video. So the pink is the eosin. We're adding acid. We can see that the calcium carbonate is turning into carbon dioxide. And then the color completely goes away, which is exactly what we're looking for. Thank you for listening. We gratefully acknowledge the support of the National Science Foundation.